today, which is Sahar that will speak about how to separate the planet signals in a periodogram from the stellar activity.
Okay, thank you everyone for setting up this conference. It's really exciting. I'll talk about periodograms and particularly about distance correlation-based periodograms. It's a work that I did in collaboration with Avraham Binnenfeld from Tel Aviv University. Who actually did a major part of the work that I'll show. Shai Zucker from Tel Aviv also, and Richard Anderson from the Geneva Observatory. Now, when we talk about periodicity detection, we often think about we hide the dimensionality reduction step. We have a time series of spectra. So the time series is generally high dimensional, and we reduce it. It could be to radial velocities or bisector inverse spans or something. And then we use this reduced time series to search for periodicity by various methods. It could be standard Lomskargel, it could be more elaborated techniques or more advanced, but we work on scalars. And at some point, what we set out to do is to see if we can use by some means, the entire information content in the spectrum without using predefined scalars. And this led to the development of a periodogram that we call the USURPER. It stands for Unit Sphere Representation Periodogram. It's available online, and so will some of the examples that I show here. You can access and try it out, and I hope it will work. But before I go into the details, I think I should introduce, at least loosely, what distance correlation is. And I will do it very non-rigorously by analogy to standard covariance. So usually when we think about covariance between two random variables, we have a nice formula and we calculate it and we're done with, but I want to think about the geometry of it, please. So let's assume that we have two random variables. We have a data set of n stars. And for these n stars, we go to our telescope and we do some measurements and we get two random variables, x and y, whatever they are. And now we can take these data sets with pairs and we can think about it as embedded in some Euclidean space, high dimensional Euclidean space. We take all the x's, we make them into a vector. And we centralize the vector in the sense that we subtract off all the means outside. And we do the same for y. So now we took the results of our experiment, and these results are embedded in a Euclidean space of some dimension n, which is the number of exposures that we took. And now the standard Euclidean inner product carries some meaning, some statistical meaning. And the statistical meaning of the Euclidean inner product in this case is the covariance up to some factor. So we have a geometrical structure that can be endowed with some statistical meaning. And the correlation coefficient could be thought of, let's say the cosine of some hyperangle in that high dimensional space. Cool. So why should we do this exercise? We do have all the formulas in it. But we are not necessarily attached to the Euclidean space. We can think of some other general Hilbert space. And if its inner product carries some statistical meaning, maybe it could be beneficial. And that's what we tried out to do. So again, we have an experiment. We have n stars. For these n stars, we've obtained some data for x and y. And now I will relax the assumption that x and y should be of the same dimension. For example, it could be the time of measurement and the spectrum itself. So spectrum is a vector. It could be maybe an image, whatever image. It's hard to compare. The issue with standard correlation is that it's hard to compare data of different dimensions. So we go through an intermediate step of a distance matrix. We have some distance functions. Whatever it is, I won't define it to the issue. They're called the standard requirements of being a distance function. And I can construct a matrix. And the matrix gives you the distance between two pairs of x's. And I can do the same for the y's. Now, this distance matrix, like before, I will center it. It means that I will subtract some value, like I subtracted the mean before. Now from each entry of the matrix, I will subtract some other value. It would be a combination of the mean of the row, the mean of the column, and the mean of the entire matrix, whatever. There are prescriptions for it. Cool thing is that these U-centered matrices, they span a linear space. And this linear space, if endowed with some inner product, in this case, this is the definition of the inner product, can have statistical meaning. And this was shown by Gabor Seki and Seki and Rito. There is a bunch of literature. Seki and his collaborators, students worked on it for a better part of a decade. I chose a couple of references that I think are readily accessible if you're interested. But the nice thing is that this inner product is the so-called sample distance covariance. And it has a nice property. Distance covariance is 0 if and only if the two random variables are statistically independent. So like before, we have a geometrical structure, and the inner product in this geometrical structure carries a statistical meaning. And it is a nice statistical meaning because it's not limited like the covariance to linear dependence. It actually measures statistical independence. But how can we make it into a periodogram? So let's think on a given trial period. I have a time series of spectra. And now I want to see if the phases of the measurements are independent of the spectra themselves. If they are statistically dependent, I have a periodic modulation. This is the thing. So a time series, now it is of different dimensions. Phases are scalars, vectors are the spectra are vectors. And we need some definition for the metric. This is the metric that we use. I won't go deep into the details, but the metrics for phi is the phase difference between two observations times the trial period minus the same phase difference. It was introduced by Shai Zucker a few years ago, and it is based on a paper by Lyons. There are some subtleties to it because it requires an extension of the theory by Seki to circular random variables. It's not trivial. And we have another metric for the spectra, which is the square root 1 minus the correlation coefficient between two spectra.
And by phase here, you literally mean the orbital phase of a planet that is proposed. There's a proposed planet, and this is great.
Yes. And now we can calculate the distance correlation, and it's the same prescription as before for the standard correlation. I just changed the objects and the inner product. But,
there's something that I haven't understood. It's probably very simple, but what does the spectrum itself represent? Is it an actual?
It's a spectrum.
Oh, so as in a stellar spectrum?
A stellar spectrum, yes. It is a vector of length whatever, of flux per wave.
Okay.
Yes.
And your difference between spectra, the distances between spectra is presumably you're doing kind of a rest frame difference because you're asking.
The difference between spectra, okay. So we take the spectra, we subtract off their means and normalize them, and then we can think of these spectra themselves as vectors pointing at some unit sphere in a high dimensional plane. And the metric that we take is the length of the string between these pointings. It's cool, but maybe we can discuss it later. And here is an example. So I will show that at least in a numerical laboratory it works. So one challenging case would be double-lined binaries if the two stars are twins. So we have twin stars of the exact same spectrum, but the velocity difference makes them to be only marginally resolved, like this. So these are the two simulated stars at quadrature. The lines seem a bit broader, the overall shape of the spectrum, and this is when the two stars coincide with our line of sight. And then the line appears narrower. And reducing these two velocities and scalars could be challenging. It's annoying. These are the simulated velocities, but the periodogram itself doesn't care about it. You can only take the spectrum, and you care about the variation of the spectrum, and you get a periodogram, and here is the correct peak. We assume 7 days, and you see that we were able to retrieve the assumed periodicity with some high significance. So it worked, at least here. Another thing that could be challenging, and I think might be of interest, is if the spectrum itself varies, not because of orbital motion, but because the star changes, and they're annoying this way. The lines may become deeper, may become shallower, may change their equivalent width. So again, a simulation, we periodically varied the effective temperature of a template star. And as you see, the lines can become narrower and shallower or deeper in some weird way. And we use the periodogram, and we again recover the correct peak. That is 10 to the minus 4 for false alarm probability. In this case, achieved by Bootstrap. So it seems very nice and well, but there is obviously no free lunch. And we've paid the price for it. And first of all, we were able to extract some periodic variation without giving very significant constraints or without dimensionality reduction, but we've lost interpretability. I don't know what caused the orbital variation. I see a peak in the periodogram. If I knew it comes from the radial velocity, I could have some meaning to it. It is a challenge. And obviously, as I think that David Hogg advocated yesterday, to some extent, if I could model the entire spectrum, it would be better. I lose statistical power by trying to be more general. And if I could have a better model, I would prefer. And there are computational issues that are on the way of being resolved. And I think also thanks to the talk to the workshop yesterday by Forman, I think I'll try it. It will prove useful, I think. So why is it good for? If I have no interpretability, maybe the model is hard. And here is an example. We can think about rapidly oscillating AP stars. Weird stars pulsate. This is an example. It pulsates in a period of 11 minutes. And it pulsates in a weird way. The abundances are weird. It's hard to identify the species. And the lines pulsates with the same period, but with different phases. So it's a challenging task. But USURPER doesn't care about the phases because the weight is defined, and we can recover with very significant without resorting to detailed modeling of the stars in the line and identification of whatever goes on in the photosphere. Okay, so this was USURPER, and we have. Again, it's nice, but again, the interpretability, especially in the context of this workshop, is important. We want to measure the masses of planets. And for that point, we've introduced partial PDC. And
5 more minutes or so?
Okay, I think I will make it. So partial PDC is, now I don't want to skip entirely the dimensionality reduction because I'm interested in it. I want the radial velocity is what I do. I need to measure the masses. But I do want to exploit other information that exists in the spectrum. Because we have geometry, it's not that hard to do. So now let's assume that we have 3 random variables. One is the phase, like before. Another is the radial velocity that we have extracted for the spectrum by whatever means that we did it. I don't know. And third would be the rest frame spectrum, the spectrum that we have shifted back to rest frame, assuming the velocity that we have extracted. So there's 3 random variables. One of them is a nuisance variable. The nuisance variable in this case is the shape of the spectrum. I want to find periodicity while controlling the effect that the spectrum variability has. And because we're living in an abstract space of geometrical stuff, we can do it. Because I can calculate a distance matrix for the velocity. And just, it's a first step in the Gram-Schmidt procedure. I can just throw out the relation, the contribution of the shape of that matrix. And then I can search for periodicity in this one. And this is what we do. So it's the same procedure as before, but because everything is embedded in some space that I can account for, I can subtract it off. And at least in simulations, again, it works. I can expand it to think about 2 types of scores. The score for a shift, if I treat the spectrum shape as a nuisance parameter, and a shape score if I treat the velocities as the nuisance parameter, and produce actually 2 periodograms. And here is an example. This is a simulated planet. Here are the assumed radial velocities in red, and we've noised it up with a simulated spot very naively at some orbital period, and you see the extracted velocities that we got after we've noised it up. There is a scatter to it. This is the typical error. And now, if you would take this and put it, say, in a Lomskagel periodogram, you get two bits. One for the stellar activity, or the stellar rotation, due to the spot, and one due to the Doppler shift. These are the results from what we call the partial periodograms in black. You see that the partial PDC, the one that accounts only for the shift, catches only the peak of the Doppler shift, and the other one accounts for the shape, it catches only that one. You should look at the lines in black. So we were able to separate between the two, and we wanted to test it on real-life sign cases, because exoplanets are hard. What we decided to do is to stretch the effect, and a scaled-up effect would be single-lined Cepheids. If we want significant variations in the spectrum and we want Doppler shift, we can make the planet into a binary and make the spots into pulsations. So we tried it out using this. That's based on Crowley measurements. Esmus is a single-line Cepheid with an orbital period of 500 days and a pulsation period of about 10 days. These are the two periodograms. Up there you can see the shape periodogram, and you see the peak of the pulsation recovered by the periodogram, and down here you see the Doppler shift, again recovered. So it worked very nice. I think I managed in time. So, wow. I talked fast because I was excited. Okay, so we talked about a couple of new periodograms, maybe 2.5 new periodograms. USURPER and the partial siblings, so on. And to convince you, I've shown a demonstration on some simulations. And it could be applied to some interesting cases, maybe relevant to exoplanets, maybe relevant to other stellar sign cases. But we are still in the phase of proof of concept, I must be honest. We need to understand how well can we propagate the information content from the spectrum to the periodogram in the end. How am I affected by signal to noise? How am I affected by the number of measurements? I don't know how to give good answers to this at the moment, and we need to work on it. Also, obviously, period identification is only a small part of the story. We need characterizations, we want masses, eccentricities, we want other stuff. And it could help, but it is not the entire story. And finally, there are other periodograms and other methods that separate between shape and shift. Recently, the Skeletal periodogram by Andrew Cameron and Eric Ford and collaborators, I think it did some very nice results. And I think the two could be complementary. I had a discussion with Ansi yesterday, and it seems that maybe we could find a way to merge between the two. This is it.
This is very nice because it really generalizes this idea of periodogram, which I love, and I like the fact that you can choose this distance measure in lots of ways. Now, imagine you get a peak, imagine you do your spectral shape periodogram and you get a peak, so you know that there's something going on with the spectral shape, and that's beautiful. Can't you then just lock down that peak and then project the data back onto the phase information at that period, and then just plot in the spectral space what part of the spectrum is contributing to making that? Isn't there an interpretation step that you could take that follows?
Well, I need to think about it a minute. The issue is that when I go through the distance matrix, I kind of lose touch with the spectrum itself.
You do.
But if I know
But now you know there's a period here.
Yeah, if I know,
Back to the pixel data and pretend.
maybe it could work.
Let's discuss it.
Yeah, I would be happy to. I need to.
I will take these first.
So you showed that the two variables do not necessarily have the same dimension, and so you can choose different distances for the first variable and for the second one. And so my question is, do you have any kind of hypothesis on these distances for the method to work, or you can take any distance, which is a distance in a Euclidean space?
Any distance that is embedded in a Euclidean space, you're fine by the theory of Secchi. But if it is not, you need to work a bit harder. Okay. This is what Shahar did in 2008.
Yeah, and so if you want to generalize the distance in the unit sphere, could you use a different local metric so that you change the definition of the geodesics? You know?
Yes, I think so. We've experimented with what was simple and yielded some results. But yes, specifically anything that, if we think about geodesics, it is, I could think about it as embedded in dimension of the surface +1, and then any metric should generally work.
Yeah, okay.
Because it's Euclidean, I think it could work. Maybe it could work better. I don't know what we would experiment.
Damien?
Apply your partial algorithm to SDT to retrieve the amplitudes.
To retrieve the amplitudes, I can only retrieve the periods.
But in partial formula, don't you show that?
So what I can, I lose a lot by using the method. What I lose is that I can only check for independence between the spectrum and the period. So I don't know what caused.
There's no way you can have access.
And not way that I can think of now, standing here. But maybe.
So retrieving the masses would then be a post-processing step.
Yes, it should be a post-processing step. Maybe there is a way to do regression, to approach regression problems using distance correlation. There is some literature. We're exploring it now, Avraham and Shai and myself. And it is a question that I don't know how to answer yet, but I'm very interested.
So how do the periods that come out of your periodogram compare against those that come from, let's say, radial velocities with the full analysis on the same data set? Are they similar, or?
When you say full analysis, what do you mean?
GP analysis combining.
So it's a good question. I haven't compared my results to periodograms that are generalized to that extent, with having some kernel that carries on some of the periodicities itself. So I don't know how to answer it.
How many spectral epochs do you need for this?
So for this one, I think 30. So we don't need that much, but it depends on the signal to noise, and I don't really know how the signal to noise affects.
Yeah. Oh, great.
Just the last one. You mentioned that all the examples you have shown are essentially stellar binaries and pulsations because exabytes are hard. So what would it take to be able to apply this to exabytes? Is it just a question of signal to noise or resolution?
So I really am not sure how good or how efficiently will the information from the spectrum will propagate into my period eventually. And we need to experiment. And I don't know, produce some other signals, whatever. We need to check it. There is no real reason for me to think that there will be no option to do it. I think it is doable. The question is with how many spectra and how well will it work. And it will be very nice to experiment with state-of-the-art spectra.
All right, with that, let's thank the speaker again.